last session before lunch. Our next speaker is William Woodruff, and the topic is building a Rusty path validation library for PyCA cryptography.
Hey everyone. Okay, well you already know the title, so I'll just sort of jump right into it. Before I get into the actual content of my talk, I want to first do a quick PSA. I know for some of you who were in the last talk, Chuck already mentioned this, but in case you weren't, there's an open space later today in room 320 at 2 p.m. Seth and Madison Oliver are presenting on the PSF's efforts, as well as some efforts within GitHub, to coordinate with the community and work on sort of larger security issues within the Python ecosystem. So if this topic interests you more generally, I definitely recommend checking it out. Cool. With that out of the way, hi, my name is William. I run the open source group at Trail of Bits. If you don't know that much about us, we're a small R&D sort of like boutique R&D firm. We do a lot of different things, but our main focuses are cryptography, compilers, program analysis research, the buzzword supply chain stuff, open source package management, security, et cetera, et cetera. And today I want to talk to you about some work that we've been doing over the past 12 months with PyCA Cryptography. Basically, I want to start by motivating. I know a lot of people in this room, if you know what X509 is, you know it vaguely is this like sort of high-level building block inside of like securing HTTP and or HTTPS and TLS. So I want to motivate why this matters, talk a little bit about X509's internals and how path validation works, talk about why it matters to make another implementation, one that is without some of the baggage of historical implementations. And then finally, the sort of journey of designing and shipping this to millions of Python cryptography users. Again, a little side journey, but this work, I work at a for-profit company, but I do open source full-time, and I'm paid to do it. This is possible because nonprofit groups, companies, NGOs, et cetera, governments funded this work. And in particular, this work was funded by the Sovereign Tech Fund. So I wanted to give them some thanks. I also wanted to thank the PyCA maintainers themselves, Paul and Alex, for scoping this work out and working over sort of 9 years of user requests to finally culminate in a design that they were happy with, that we then built for them. And I also want to ask, or rather thank, Filippo Valsordo, and then my colleagues Andrew Facundo and Alex for designing and engineering components of this work. The big banner item here is that Python cryptography, which is sort of the de facto standard library for higher level and lower level cryptographic building blocks in Python, now has X509 path validation APIs. When you pip install cryptography, like many of you already do in your code bases, this will work right out of the box. It's written in Rust like the rest of X509's, or Python cryptography's X509 core. It's only about 2,500 lines of code, new total. And with a small sort of qualifier, there's no OpenSSL involved in this. It is pure Rust in the path validation process. You can use it today to replace your legacy uses of pyOpenSSL and other path validation libraries. And for some of you who know X509 already, but for those of you who don't, X509 validation is actually pretty scary. So we were pretty scared when we wrote this thing. So we tested the crap out of it. We wrote an entire new test suite that we call X509 Limbo for testing and comparing various path validation implementations. And in the process, we found a bunch of bugs in other implementations. And so this work has already informed development efforts on Go's implementation of X509 validation, as well as a few other Python implementations. So I think that's pretty cool. But to take a step back, you might ask, like, why does this boring crap even matter? Like, I don't care about the stuff below HTTPS. My users are mostly interacting with like my REST APIs, or they're interacting with like my web interface, or they're interacting with sort of like things that are way, way above this part of the stack. And the basic answer to this, that the way I like to think of it is, while you and your users sort of sit nicely on this like layer of relatively sound abstractions, all of the security assumptions that make your system safe to use across untrusted networks lie beneath. And so that's things like TLS and X509. And I recognize that the order here is a little bit wonky because X509 is really above TLS in some sense, but that's sort of to emphasize sort of how deep in the stack these assumptions are. X509, I sort of jumped the lead on it, but X509 is the sort of building block for a lot of the table stakes that we have on the modern internet. So HTTPS, which itself is built on TLS, is sort of the kind of in an amazing way, the current assumption for what users expect when they connect to websites. They expect to see that lock. They expect that their traffic is private between them and the entity that they're connecting with, meaning that even if they don't necessarily trust that entity, at least no other middleman or middle person can get in the way and read their traffic. But this has a fundamental chicken and egg nature to it. To securely connect to a server, I have to know that server's public key, the thing that allows me to encrypt traffic to them. But I want to connect to arbitrary web servers that I haven't connected to before, and that means that I have to obtain their public keys somehow. But to securely obtain them, I have to talk across the network to a server to get that public key, which means that I need to securely connect to a server, which is what I was trying to do in the first place. And X509 exists in part to solve this chicken and egg problem in network security. So to sort of dive into it, at its most basic level, X509 is a public key conveyance and identity binding format, which is a big, complicated way of saying that you have some public key and you have some metadata that you want to attach to it, such as a username or a domain name or an IP address. And you sign over that data using the public key's private half, and you ship that across the internet, or you make it publicly available so that people can, when they verify things with that public key, they can also assert that it came from some identity that it claims. Of course, you don't know that you trust that identity necessarily, or that it is a true identity, because you're just receiving a certificate. You don't know why you would trust its assertion that it belongs to freestuff.example.com, for example. But the critical thing here is that it binds metadata to a private, or to a key pair. So that's the most basic level. X509 is also a chaining primitive. Because it can be signed by any public key, not just the public key that, or rather, it can be signed by any private key, not just the private key that's signed for, that corresponds to the public half. You can have certificate A signed for certificate B, and therefore convey the public key for B. And the nice thing about this is that because the metadata is disjoint from the key itself, it's not a one-way certificate to key mapping. A single CA can have multiple key pairs, each with its own certificate, which they all have the same sort of CA name for rotation purposes or just because. And also a single key pair can have multiple certificates. For example, if you want to renew a certificate's public key without rotating it, or if you want to issue a key across multiple CAs, so that you have like a web of trust, depending on what roots are installed on a user's computer. And this diagram is just sort of like the most basic example of that using Let's Encrypt's chain. So you have how should I say this? So you have the root, which is the root of trust, and that contains both a self-signed root, meaning one that signs for itself, and also one that is signed for by a higher level root. And so you can have either of those in your root of trust, and you can still establish a chain to something trustworthy. To go finally, the next step higher, X509 is also a protocol for securely introducing principals, meaning sort of entities, to each other. Chaining allows us to go from that local set of trusted entities, which comes with your OS or your language distribution, to a remote untrusted entity that is attested for by that chain of signatures. And this is true for TLS, like website connections where you want to go to example.com, but it's also true in the opposite flow, where if a website wants to authenticate that a specific user is connecting, that user can present a certificate that chains back to a bundle of trust for user identities. And this is common in like mutual authentication land. And the really cool property that sort of comes out of all of this is that principals can be introduced through untrusted intermediates, meaning that as long as I can ultimately form a chain to my root of trust, I don't actually have to know that the intermediates being served by my connection from the website are trustworthy. I just need to assert ultimately that they chain back to the thing that I already consider trustworthy, because cryptographically, as long as they can sign, I sort of assume the integrity of the connection. And then finally, last but not least, X509 is a complete dumpster fire of an ecosystem. 75% of the world runs on OpenSSL and its forks, meaning things like LibreSSL and Boring. These forks are often significantly better than OpenSSL in terms of sort of security practices, or have been historically, but are themselves severely constrained by API and ABI compatibility with OpenSSL, because OpenSSL is the default assumption in a lot of code bases for how to do secure socket connections. Because OpenSSL is so old and has so much sort of legacy baggage associated with it, the implementation of X509 in it is sort of this combination of half RC 3280 and 5280, which I'll get into what those mean later, and half just like whatever was there when it was created. And there's a lot of other stuff out there. There's the other sort of 1/4 of X509 implementations in the wild are things like Embed TLS, WolfSSL, GNU TLS, and then a whole lot of like vendor stuff that isn't really maintained and exists on middle boxes that nobody really monitors or patches. And what this means is that not only are these things not only do these things have a spotty security record, but it's also hard to evaluate sort of the compatibility layers that you have to go through, because a lot of these things don't adhere to the best practices that we now know for the internet PKI. So you have to make compromises when you build a new path validation library to be compatible with some middle box somewhere in your stack that you have no ability to patch or even really monitor. And as I sort of hinted at, X509 is also a playground for exploitable logic and memory safety bugs. There's sort of this geometric combination of dir parsing, which is sort of notoriously difficult, especially when you combine it with burr parsing, as well as a variety of ways to make X509 itself insecure by stating the wrong policy or including the wrong extensions or missing extensions. And the severity of these problems ranges from remotely triggerable denial of service, which is pretty bad, but not the worst thing in the world, to false positive verification, where you can get someone to trust the wrong certificate, which is very bad because now you're potentially doing a man in the middle, to remote disclosure of memory, of process memory, which is extremely bad because now you're leaking the original secret key, so you don't even have to impersonate the certificate. And that's exactly what we saw with Heartbleed back in, I believe that was like 2013. And then to make things even worse, some of these bugs that I mentioned are actually baked into the specs themselves. So the spec itself encourages you to implement path validation in such a way that makes geometric explosion or polynomial explosion during parsing very, very easy, which is unfortunate because people use the specs and assume that they're safe. So this should all sort of lead to the question, which is, can we do X509 better? And specifically, can we do it better for the Python ecosystem? And at this point, you might think, well, these are historical issues. We sort of know what they are. Why don't we take existing code bases, which are sort of have a lot of scar tissue and have a lot of eyes that have looked at them for vulnerable or valuable bugs, and try to build a safe interface on top of them? And this is sort of what already exists in the Python ecosystem. So the studlibs SSL module is closely tied to, or is built on OpenSSL, but it has some deficiencies. One of those is that it's closely tied to SSL and TLS themselves. It's not a generic implementation of path validation. This doesn't always matter, but it does matter in cases where, I mean, the world is bigger than just TLS. You have companies and nonprofits that have their own internal PKIs for things like VPN deployments, and these things don't necessarily adhere to the rules that the web PKI does, and so they can't use the SSL module. There's also pyOpenSSL, which provides a generic and safe from the Python level, meaning no memory safety issues, API for path validation. And it's even lower level and more implementation specific than SSL is, but it is usable and it's mature, and you can get away with using it. But I want to reiterate, I mean, you can do these things, but building on OpenSSL means inheriting a lot of baggage. It means inheriting the spotty security history, a lot of really bad defaults. So for example, in pyOpenSSL, I'll talk about this later, but there's a lot of flags that you have to set if you want a thing that resembles a modern path validation algorithm. And those things are not set by default because they can't be set by default, because too much stuff assumes that the old bad defaults are present. Performance tar pits. We'll talk again about like how we were able to radically improve the performance of X509 validation within our implementation just by moving away from key parsing in OpenSSL, not even the cryptography parts, just the parsing. And then finally, OpenSSL, while they do have really strong ABI stability commitments, they don't guarantee as much on the API level. And so you have this baggage issue of every time OpenSSL changes, you want to go back in and update your bindings to match what they do. And this all boils down to a set of conditions that we really don't want it to bear for our implementation. We want a clean slate to build a confident, sort of like fresh implementation on. So I want to talk a bit about the design principles for our implementation before I even go into the details of it. Above everything, I don't think anybody really calls them Sleevy's laws, but I think of them this way. Ryan Sleevy has this blog post where he talks about sort of the right ways to do path validation. And one of the key things that I think a lot of implementations miss is that there is no one true chain. As engineers, when we think about X509, we think like, oh, there's a chain of trust to the root, and the root is a root certificate. But in reality, the chain is a graph that you traverse over. It's ideally a cyclic directional graph, but in practice, we'll see that sometimes it isn't. So you actually have to traverse that graph and consider multiple candidates before you ultimately settle on a single chain of trust. And that is the final chain, but that's really not the core algorithm itself. On top of that, the process of discovering those candidates within the graph, many implementations treat it as a static problem, where you start with a set of constraints at the top, and you follow those constraints down as you traverse, and you end up with a chain. But in reality, it's actually a dynamic depth-first search problem. You have these things like name constraints, which get accumulated as the chain gets built, and you need to reject candidate chains, even if they were previously valid, if a new name constraint invalidates components within those chains. So things like that are actually pretty subtle, and they change fundamentally like the architecture that you design for an X509 validator. And many legacy validators don't even, they didn't think this way, and then they ran into invalid chains, and then they sort of patched things to make it look correct. Another really important thing I want to talk about, which is kind of subtle, is the idea of encoding rejections into the search. A common bug that you see in especially older versions of OpenSSL is that OpenSSL would perform path validation. It would go through the graph, and it would find a chain, and that chain looks great in terms of all the constraints that were specified. But then you would get to the end, and it would say, does this chain match the domain example.com? And it doesn't. So now OpenSSL says, well, that's obviously not a valid chain, so I'm just going to fail the entire process. The problem with this is that there might be another chain in the graph that does satisfy example.com, but you don't know because you haven't encoded that rejection into the chain search itself. All you've done is found a chain that looks mostly good, and then you've rejected it, and then the user doesn't know that there are potentially other chains within their trust root and the intermediates that get them to the cert they need. This is a huge reason why, for example, I believe it was OpenSSL 098 had to be sort of like shed from a lot of ecosystems because it just fundamentally did not handle rejection sampling or rejection correctly. And then finally, I call this like know your limits. The PKI or X509 chains in general are a truly abstract data structure. I mean, it's a graph, it can be arbitrarily large, it can have an arbitrary number of constraints. But in the real world, the web PKI is almost always no deeper than like 5 certificates in a graph. So in practice, you really don't need to open up your API surface and your implementation to all kinds of sort of explosions in complexity or explosions in compute. In practice, you can set actually pretty conservative limits to chain depth, name constraint, evaluation, etc., without breaking a single thing on the internet. And in fact, the only things that you will see that would break are things that are intentionally trying to break your implementation, so you should reject those things anyways. But again, many older implementations simply say, well, my goal is to find a route through this graph, and so I'm just going to keep trying until I find it, which means remotely triggerable denial of service. Yeah, so those were the design sort of principles that we worked with. I also want to talk through a couple of design constraints. So one of them is there's 3 of them really. There's minimality, correctness, and speed. In terms of minimality, X509 is a huge ecosystem. It was first standardized in the mid-1980s, and it's not an exaggeration to say that really the only good parts started to appear about 15-ish years ago. Before that, there was a lot of sort of mystery of like people just doing whatever they wanted with the certificate formats, putting whatever they wanted into them, not really having sort of strong policies around maintaining or securing their private keys, etc. The result of this is that there's this massive proliferation of what we call profiles in X509, which are the different parameter sets that you can configure when validating or building chains. Almost all of these are bad, and we don't want to support them because almost always supporting them implies weakening the normal correct set of defaults that the web PKI relies on. So this means really we only want to implement the parts that people actually use and care about. On the correctness front, as I mentioned, path validators in general, especially legacy ones, tend to be extremely buggy. They tend to not handle things like self-signed certs or self-issued certs correctly or name constraints correctly in all cases. This unfortunately means that there are some real-world chains that exist that users expect to satisfy that we need to that are broken in some way according to the actual profile, but that we need to support. And as a result, we have sort of like we set out when we designed this to have like basically a bug budget where we said like we will, if in the real world as we test this thing we observe real chains that should exist that don't satisfy the constraints of the profile, we will set out to explicitly allow those things because we know that other validators for legacy reasons expect those to validate. And this sort of falls into what I've mentioned with like building confidence empirically with tests as well as testing other implementations. So when I say like, oh, this path validates on another implementation, we want empirical evidence that we can show to the public that says this is why we chose to make this decision in terms of the profile construction and why it's not strictly RFC 5280 or CA browser profile compliant. And then this was all made easier by the fact that the Python cryptography maintainers are sort of like test freaks. They rightfully require 100% test coverage on all their changes. And so this really pushed us in the right direction from the very beginning to make sure that everything we built was fully tested. And then finally, for speed, the really only thing I want to say is we want to be faster than OpenSSL. And you might think this is really hard because OpenSSL is C. It's got 30 years of development behind it. It turns out it was actually really easy. So I'll get into that later. So just to go into a bit of detail on minimality, in practice, there are really only 2 X509 profiles that matter for almost all PKI uses in the wild, and especially for Python users. And these are RFC 5280 and what I call CABF, which is the CA browser TLS basic requirements, which is a mouthful. RFC 5280 is sort of the default blanket profile for all PKIs, all modern PKIs, for X509 v3, which is the newest version of X509. And then CABF is built on top of RC5280. It's mostly a superset of it that basically ratchets down further the requirements to make sense for domain certificates, things like IP certificates, as well as profiles like extended validation or organizational validation for corporations and entities. Limiting our approach to just these two profiles has some pretty significant benefits that we observed in the practice of doing this implementation. One thing it allowed us to do was outright reject the overwhelming majority of key and signature pairings that actually occur in the wild with X509. These things occur in the wild, but they're not very common. Like I said, they don't affect ordinary web and like internet PKI applications. But you do see all kinds of sort of bad things like explicit curve encodings in certificates. Most notably, the International Civilian Air Authority, I believe, uses explicit curve encodings in their certificates, which are very easy to misuse. And we just outright reject those things in terms of what CABF encourages, which is, in practice, ECDSA and RSA, and then maybe sometime in the future EDDSA, which I know you don't necessarily know what those are, but those are three relatively conservative modern cryptographic signature scheme choices. Another nice thing that allows us to do is it allows us to hard reject older X509 formats, such as X509 V1, and the well-known security pitfalls that come with those formats. These things include like malformed subject alternative names, serial numbers that are 0. I'll talk about why that in particular is pretty bad later. So basically it allows us to carve out a lot of the stuff that legacy implementations have to bake into their design. I'll talk a little bit about correctness as well. So as I sort of mentioned, the actual abstract process of building a chain in X509 validation is actually kind of beautiful. It's like a abstract depth first search over this acyclic graph of your leaf certificate, which is like your domain certificate, through a set of untrusted intermediates, terminating at a root certificate in your root of trust. And as you search, you do this dynamic stuff, which is a little weird, but it's fundamentally consistent with the depth first search process, which is you apply path length constraints, like saying some certs say that like I shouldn't have any more certificates below me, and so you check those constraints. You check name constraints to make sure that you're not allowing an intermediate to attest to a certificate that it says it should never be allowed to attest for. And then finally, you return the first full chain you find, but if you don't find a chain initially, you keep sampling until you exhaust all possible candidates. So this is sort of like a pristine, beautiful algorithm in theory. But in practice, it's not really that pretty. In practice, attackers can actually force cycles in this theoretically acyclic graph. This is a classic source of denial of service or uncontrolled recursion in X509 implementations. And the reason for this is that many implementations will perform the graph traversal based on the subject name that's encoded in the certificate, which is that metadata I was talking about. But the attacker can control that. It's just metadata. It's just plain text. They can insert whatever subject name they please, and then if it, of course, results in a cycle in the graph, your implementation will spin until it stack overflows or just spins forever. Another source of sort of theoretical cleanness that in practice is pretty ugly is path len and name constraints. These are widely used by some CAs, but in practice, everything outside of the really well-trodden path with these constraints is pretty buggy. There are these things called self-issued but not self-signed certificates in the web PKI, and when these occur, implementations historically don't respect the path len or name constraints, or rather they fail to not respect them, because the spec says explicitly that you shouldn't honor those constraints on those ones, but they do anyways, and so you end up rejecting chains that are potentially valid. Another thing that's actually even more sort of concerning is that in the real world with the internet, there are actually incomplete chains that are present on actual websites. As I mentioned, you're supposed to serve both your pure certificate, which is your example.com certificate, as well as any untrusted certificates that are needed to build the chain to the root of trust. But in practice, a common source of bugs is that people will set up certbot or a similar tool for automatic issuance, and then they will forget to include the generated intermediate chain in the TLS response that's sent to clients. And what that means is that the server, or rather the client, ends up seeing the pure certificate and then their root of trust, and then there is no intermediate to connect the two through. And so clients like Chrome and Firefox do all kinds of nasty hacks in process where they monitor the world's intermediates and build up a cache of intermediates they've previously seen. And this is like a disastrous hack, but remember, it's fundamentally sound, because as long as you change your root of trust, it doesn't matter what's in the intermediate set. And so it's kind of scary, but it's safe in practice. But it's another one of the ways in which path validation is really not as trivial as it seems on paper. And then finally, as I mentioned, there's this issue of like rejection after search, which is many implementations will give up after finding the first invalid chain candidate. And this in practice means that many clients will send intentionally limited chains to prevent a well-known failure path in, for example, legacy versions of OpenSSL, which is not ideal because it means that it's harder to upgrade algorithms, it's harder to upgrade and rotate certificates in the web PKI. Okay, and then last but not least, in terms of sort of design constraints, performance. So one nice thing about X59 validation is that path validation is largely dominated by parsing and profile validation, not the cryptography itself. This is true whether it's RSA or ECDSA, but especially true for ECDSA. The bulk of the work is parsing the DIR, building up your chain, doing this recursive depth first search, and then validating on each step, and then potentially doing like this chain explosion where you initially sampled and you found an invalid chain, you have to keep searching. So that can be somewhat expensive. The cryptography itself isn't. And as a result, when we built this implementation, we really focused on things that we knew would be sort of performance potholes in the design. And so one thing we emphasized was that the hot path for path building, meaning everything outside of the sort of like top level user APIs, is in compiled pure Rust. So once you start doing the path validation process, you're jumped straight into Rust with a small amount, basically as small amount as possible Python interpreter overhead, as well as other places where like you would have to interact with cryptography, or rather interact with things that would slow down the path building process. As part of this as well, we cache parse and raw keys aggressively. A common source of issues is that like as you backtrack, you have to reparse the key that was in an old partial chain and then recheck against it. So we cache things like that. We also minimize the number of scans you have to do over the extension set for X59, which, again, I know if you don't know X59 doesn't mean a lot to you, but basically it's a linear set. And so if you have these huge graphs, you end up doing like a linear cycle many times. And so you want to cache that and minimize the number of searches you do over that set, which can be not huge, but large enough to make a difference. And then finally, and kind of most importantly actually, originally when we designed this, one thing we did was we called back into OpenSSL via Rust OpenSSL, which are safe wrappers in Rust for OpenSSL, for subject public key identifier unpacking. And the subject public key identifier is the public key inside the certificate. It turns out that this alone, replacing this with our own pretty small SPKI parser, made the entire path building process 60% faster. Not just key parsing 60% faster, but the entire path building flow for average web certificates became almost half over, or more than half over as fast as it would be for OpenSSL, which is nuts. Okay, so that sort of goes through the sort of design principles and motivations we had. I also want to talk a little bit about actually shipping this thing. So I've heard X59 validation described as the like the electric third rail of public key cryptography. It's a thing that nobody wants to do. It's sort of a fundamentally scary thing to do, because when you mess up, you enable men in the middle or all kinds of other really nasty attacks on the public internet infrastructure. Reasonably so, a lot of cryptographers or professional cryptographic engineers shy away from this as a problem because of how sort of serious it is. As you might understand, we were also reasonably afraid when we did this with this approach, and so we really wanted to design it or test to a sort of absurd degree of confidence everything that we designed and built. And what this meant in practice was we sought a more general approach than one-off unit tests. Ordinarily, we would work with our clients to build up to 100% test coverage by handwriting tests and then generalizing, parameterizing tests where possible. But with X59, you have these really complicated graphs where you might have these constraints that need to be tested deep within the graph, and it's really tedious to write one-off or even parametric unit tests for these things. So we want to be able to express those kind of complex graphs, as well as graphs that fail deep into validation, somewhere deep in the intermediates that then needs to be asserted for. We also want to categorize tests. We want to say this test is important for web PKI certificates, whereas this test is important for RFC 5280, which is the sort of subset of the web PKI. And then finally, even if our tests pass against our implementation, we don't know that our implementation is correct modulo other dominant X59 validators. And so we wanted a way to generically compare our implementation to other implementations that are common in the wild. And this is needed for both doing better than those existing implementations for the reasons that I mentioned, but also for that bug budget reason that I mentioned, where there are certain things that we know we would need to be compatible with because there are too many things in the wild that just depend on those things. That is why we designed X59 Limbo, which my slides will be available at the end of this talk, but essentially X59 Limbo is a generic test suite and test vector format that we designed that can be applied across multiple implementations of X59 validation. Contains basically a list of test cases, and each test case contains a graph of chain state as well as the expected result for that graph, meaning whether it's expected to fail, whether it's expected to pass, whether it might be a denial of service that we want to, even if it's valid, still fail because we don't want to enable clients to build these computationally intensive graphs. It all gets built in this giant JSON blob. And then it also contains third-party tests that we integrated from other TLS test suites. So for example, Netflix has this fantastic test suite called Better TLS. And we pulled those down, reconstructed them into our test suite format, and then allowed both our implementation as well as third-party implementations to consume those in a unified manner, which was pretty helpful for finding some bugs in other implementations as well. And then finally, it's also grouped into namespaces. So for example, we have this WebPKI namespace for the CA browser profile. And this text might be a little bit small to see, but this is sort of what it looks like. We have a website called x509-limbo.com. And if you go to that website, you can see both the test cases themselves as well as the results for various implementations that we have harnesses for. And so I know it's kind of small, but in this case, you can actually see that Go cryptography unexpectedly validated a chain that we expected to fail. And so we submitted this as a bug, and they created a patch for it. So this has enabled us to generically test multiple other implementations. This, as I sort of hinted at, was the key thing that allowed us to get to 100% coverage without too much manual test case work. And in the process, helped us find a bunch of bugs in other validators, including one CVE so far, which is a memory corruption CVE, which you really wouldn't expect to find when doing the sort of like abstract graph process. And yet, in GNU TLS, we found an arbitrary mem copy that was triggered by one of these test cases. Yeah, it's kind of small, but I'm also happy to talk about that later as well. Another thing on sort of like the shipping side of things, I want to talk a little bit about the API design that we settled with. On top of all of the sort of like things that make X509 validation fundamentally dangerous when you implement it, there's also all kinds of risks that come into play when you expose validation to users. Users, even if they conceptually understand like the chain and the idea of like a root of trust, they don't always understand how to encode their actual constraints into the API. And this is especially true for OpenSSL, where there are a lot of there are many, many options, many of which are legacy options that do uncontrolled or unusual things that aren't necessarily profile compliant. So we wanted to sort of minimize the number of options that a user could set and help them avoid overly conservative searches. Another thing we wanted to prioritize was sort of this concept of like fluency rather than flags for options. And then I suspect that very few people in this room will know, but does anybody happen to know what X509V X509V flag partial chain does in OpenSSL? It's kind of unusual. Like, okay. You might think that setting that is insecure because partial chain, you don't want a partial chain, you want a full chain to the root of trust. That flag actually enables the correct path validation algorithm in OpenSSL. What it does is it tells OpenSSL to stop searching once it hits the root of trust, which for whatever reason OpenSSL calls a partial chain. This is the exact opposite of what every other implementation does by default. And this is not set by default in any version of Python until Python 3.13 because we added it. So this is the kind of thing that like, you don't really notice it, but it does have an effect on the overall sort of correctness of the WebPKI. Finally, we also wanted to like emphasize domain separation as a concept in the X509 validation, like the public Python API for this stuff. Critically, there's both server validation and client validation on the public internet, and the two have very different profiles and also sort of paths. They look different ways. With server validation, you give it a domain name or an IP address, and you expect to find a chain that ultimately builds up to that domain name or IP address. With client validation, you give it a client certificate, and then it returns a list of identities that you should match against your database or whatever else to see if that identity is one that you trust. And conflating those into a single public API means risking that users don't encode their DNS name for server validation and then blindly trust any client or any peer certificate they get given. So we wanted to separate those two sort of like domains of interest into separate APIs. And similarly, something that has happened in the past with X509 APIs is that the trust root is often encoded as like a sort of a sequence of X509 structures or other sort of like public key structures. And this data structure shares the same shape as the intermediate set. And so users will swap the two in their API calls. And so you end up building to the intermediate set rather than to the trust root, which means, of course, that the attacker controls the entire chain, and you are now vulnerable to man in the middle, or person in the middle. We wanted to mitigate this, again, by performing domain separation between the types by giving trust roots and anchors their own discrete data type to prevent confusion with untrusted intermediates. And this is what that looks like. You'll note that it's a little bit verbose. I mean, we have to like manually load the store, manually construct it. In this case, we load it from Certify, which is a PyPI package that contains the Mozilla root of trust. We then build a policy builder which contains that store, contains a validation time. The validation time, of course, should be the current time by default, and is the current time by default. But you can also backdate it if you have certificates that you know were valid at a point in time, and you want to validate at that point in time. And then finally, we explicitly construct the server verifier, which contains the domain name that it should be bound to, and then finally verify the pure certificate against its untrusted intermediates, modulo the store, which is part of the verifier via the policy within it. So that's it. This exists today. Like I said, you can pip install cryptography, and also if you go to the cryptography public docs on cryptography.io, you can read the full public documentation for this work. Finally, I want to talk a little bit about the lessons we learned, as well as some of the future work we've been thinking about that came out of this roughly 12 to 16-month process we went through. One of the big lessons that we learned was that the RFCs and the CA browser forum documents, they say one thing about how the chain should be built, and then, as I sort of repeatedly said, implementations do a completely different thing. For example, the CA browser forum documents say that you should always prefer the subject alternative name, which is a modern way to encode the domain name or the IP address and certificate. In practice, many implementations also check the subject, which is the old way to encode the domain name or IP address, or they check both and they do weird things that the two don't match. Sometimes they pass, sometimes they fail, sometimes it's not defined. This is a source of ambiguity that is sort of non-ideal, and we intentionally, for our validator, only stuck with the subject alternative name. We do not validate the subject because CA browser forum says do not validate the subject, and this is what the WebPKI does. Another thing that we noticed is that many implementations do not bother with serial number checks. A serial number, in principle, is supposed to be a unique string of bytes in the certificate that is supposed to correspond to some internal database within the certificate authority that gives them the ability to sort of track what certificates they've issued. In practice, a lot of certificate authorities would just use like a Unix timestamp with like incrementing by seconds or milliseconds if they needed to for fidelity, which resulted in a pretty famous CA compromise or not compromise, but a CA impersonation attack back in 2008, which allowed the Flame malware to spread. After that, the CA's browser forum got together and said, like, you really should check that the serial number is 20 bytes long and should be random or look random. But many implementations still don't bother to check this. And so many implementations are, at least in principle, still vulnerable to the same kind of like serial number confusion or serial number impersonation that enabled Flame back in now 16 years ago, which is not great. Another thing we learned is that most implementations have at least one name constraint bug causing false negatives during chain construction, meaning, again, overly conservative searches resulting in no chain where a chain should have been found. And this was almost always found during cross-issuance or self-issuance. So as I mentioned, X59 has this property of being able to cross-issue across multiple authorities. And we found that when those authorities had name constraints attached to them, you would often fail to build the chain with OpenSSL or with GNU TLS, for example. And that's just, again, not ideal because it means that the WebPKI cannot move forward and further ratchet down on name constraints as a valuable way to limit the scope of a certificate. And so we put a great deal of effort into fixing that and making sure that our implementation was almost entirely compatible with what CABF says in terms of how you should handle name constraints. And I'm happy to talk about how we aren't compatible too, because there's still some edge cases. Similarly, with pathlength constraints, almost all implementations fail to handle them correctly when a certificate is self-issued but not self-signed. And then finally, most implementations ignore or don't enforce the presence of the subject key identifier and authority key identifier. And in practice, this one sort of matters the least of everything that I've said because they are just sort of hints designed for optimizing chain building. But they sort of indicate the general like level that the ecosystem is at in terms of the sort of maturity of their conformance with the specifications. On top of everything that the standards say or don't say, or that implementations do or don't do, modulo the standards, X59 itself has lots of quirks that the community continues to sort of lawyer over and that manifest in strange ways in terms of how chains are actually built in the wild. X59 is very explicit. It says that you should really only have 20 octet maximal serial numbers. But sometimes when you randomly generate a number, the top bit is 1, which means that it's a signed integer, which means that it's negative. And dir encodes 20-bit signed integers as 21 octets, because you now have a sign field. And so the question is that a valid certificate or not? It turns out most implementations, like almost every implementation that I saw at least, has a comment that's like, ugh, we found one, for now let's allow this. And nobody really can agree on whether this is correct or not, but in practice every implementation allows it because it's not a huge issue. Another sort of challenge is that RC5280 doesn't respect the laws of mathematics. It says that 0.9 repeating is equal to, or is not equal to 1. And this matters particularly because you might have an expiration time, and that expiration time is only resolved to a degree of seconds. And so what happens if you were at that second 0.99999, or obviously not infinite, but point that? Well, RFC 5280 says, oh, you just chop that off, and it's the previous second, even though it rounds up to the next second. And there have been actual revocations performed over the semantics of this, even though it's just a single second. Another sort of weird thing that people don't really think about in the X59 ecosystem is that everybody, when we talk about X59 publicly, we talk about like root certificates and like the root certificate store. This is kind of like a lie. It's an abstraction that we use to talk about the root of trust. In reality, the RFCs for X59 only talk about trust anchors, which are public keys with names, which means that they are sometimes conveyed as X59 certificates, but they aren't really necessarily certificates themselves. This is confusingly directly in conflict with what CABF says, which is CABF never uses the term trust anchor. They only ever talk about root certificates. And so even though the two are ultimately sort of semantically conflatable, they're conceptually different things, and they have different approaches to them. Like, for example, with the trust anchor, you don't have to have X59 inserts. You could have just a new ASN1 structure that you define for your trust anchor. And then a whole bunch of other things I really don't want to go through. There's a lot of things like, you know, if you convey a trust anchor as a certificate, does that mean you respect the constraints that are encoded, or because it's trusted, you don't care what it encodes because it can encode anything? That's just not defined really anywhere. We chose intentionally to respect constraints on roots because the theory is, well, if the user controls the root, they probably meant something by putting those constraints on their root certificates. We don't want to ignore their intentions. But some browsers do or don't some of the time, depending on which path they go through for their validation. So this is another source of sort of ambiguity in the ecosystem. And finally, it's also unclear whether the leaf's public key is subject to constraints around key strength or key type. CBF is very explicit that you should only use RSA and ECDSA, but the leaf itself conveys its own public key for actually encrypting the traffic, or encrypting the initial connection to the website. It's not clear whether that public key is also constrained by the requirements. It just doesn't say. And so we chose to constrain it, but some implementations do not. And that is, again, a source of sort of larger ambiguity. But the overall picture that I want to wrap up with is that despite all of this, both on the standard side and also on the format side, things are actually pretty good in the X509 ecosystem. At least, if not pretty good, they're much better than they were a decade ago. The Web PKI is in much better shape thanks to technologies like certificate transparency, as well as ratcheting down the validity of certificates, going from like multi-year valid certs to ones that are only valid for 90 days by default, with, for example, Let's Encrypt. And more generally, users just have higher expectations around how the internet functions and how secure their connections are. Users now expect that lock. They now expect, at least more technical users, they expect that they aren't being man in the middle by some mystery CA in their bundle that is issued for their cert. And CT allows them to enforce those things. The browsers themselves also sort of gotten their act together and have become much more serious about their role in enforcing the strength of the Web PKI. They now have sort of put an end to all the sort of mysterious practices that CAs used to get up to, such as like BUR certs or V1 roots or all these other things. And even today, there's only a small handful of invalid serial numbers left in the public in the web public key infrastructure, which is fantastic. But these things still do exist. They still are problems, and they are especially problems in corporate settings or private settings where you have your own internal PKI. And so the hardest part of all of this was, again, determining that break budget versus other implementations. Really not the actual code itself, because like I said, conceptually, when you follow the modern specs, it really isn't that dangerous. And you test, it's really not that dangerous. But I don't want to say it's not all rainbows and sunshine. Some bugs did still sneak through on our initial merge of this. I mentioned that the leaf public key isn't necessarily constrained by strength checks. The root public key is, but we didn't check that. We found that with a test, which Alex was like, hey, that sounds wrong. Why aren't we checking this? And I was like, oh, I write a test for it. All the other implementations did it. We didn't do it. That is a strong signal that it's a bug in our implementation. We had a bug where we would simply ignore name constraints that we didn't know about. So if they were a type that we didn't know, we would ignore them rather than rejecting them, which many other implementations also do. But the spec is clear. You have to reject things you don't know for name constraints. And so we added that. And then Python has sort of like two flavors of datetime objects, ones that are naive and non-naive. And we ran into a bug where our datetime objects, not even within our API, but within other parts of Python cryptography, they would take a non-naive datetime object and naively truncate it to UTC. So even if that time zone, even if the time encoded in that time object was for another time zone, it would become the same time within UTC. And that would mean, in theory, that you could have slightly longer validity or slightly shorter validity periods than you'd expect for a chain. And each of these, as I said, got their own new X59 limbo test case, revealing bugs and other implementations in the process, which I think is the ideal outcome. Last but not least, I wanted to mention some future work we've been thinking about. As I hinted at, there are other profiles besides RFC5280 and the CA browser forum basic requirements. There are things like Intel has a custom X509 profile for SGX. Microsoft has one for Authenticode. They all tend to be based on the same baseline, but they have little variants. And users often ask for these things. And so we've been thinking about ways to enable these without compromising the overall security of the best path. Users also want more control over which key and signature algorithms they're allowed to use, which is often a bad thing, but sometimes it is a good thing. For example, we don't support DSA right now, but that is a reasonable, sound choice for a modern PKI, and so we should probably enable that at some point. But again, the larger guiding principle here is we want to make the current APIs. We want to make the current APIs as easy to use and make sure that any future changes we make do not compromise that usability path. And then finally, we want to work on revocation APIs. We took the same approach as Go, which is we just simply did not consider revocation for this design. Go's validator doesn't look at revocation. But in the future, we want to add APIs for checking CRLs and OCSP responses, etc. And then last but not least, we want to spread the gospel of X509 Limbo. Get more implementations to adopt it upstream. We have lots of in-repo harnesses, but we want to bring those harnesses further up into each implementation so they can check it as they merge commits. And then cannibalize additional X509 test suites and integrate them into Limbo. And then finally support profiles other than 5280 and CABF. That's everything I have. I have literally 1 minute for questions, so if anybody has one, I'm happy to take it. But otherwise, thank you very much. I think there are, if you do have a question, there are 2 mics, but otherwise, like I said, please just find me after the talk.